So now that we know about intermolecular forces and gases, we can talk about vapor pressures. Vapor pressures are um, uh, very important to understanding boiling points and are used a lot in organic chemistry for separation techniques such as distillation. So you gotta be able to understand this, and that's why we're covering it now. You'll see it again in second semester general chemistry as well. So if we look at a container that has a liquid and it has a lid, so we have a liquid surface. This is a closed lid, so it's a closed container, um, and we have liquids molecules here. Now, liquid molecules are free to move around in our solution, but they are constantly having interactions. So we have these fluid dynamics, but think of it like the molecules are holding hands, and they can kind of go from one hand to another and switch back and forth. But there's always kind of connections to other molecules as there's movement. So liquid molecules are free to move around. In the gas phase, we can have molecules moving around, but there isn't that intermolecular interactions, especially at lower pressures. Now, we can have a molecule that goes at the liquid surface up to the gas phase, and we can also have gas molecules as a gas phase hit the surface and go to back to the liquid phase. So this going from gas to liquid or from liquid to gas, this is evaporation, and to go from a gas to a liquid, that is condensation. Condensation. Okay. Um, and so we can have different rates. If you have a closed container, then you tend to reach an equilibrium where the rate of evaporation and condensation equal out. But it should be noted that that can change if you have an open container. That's why when you leave your glass out at like on your bed stand, if you come back, a week or two later, the water might all be gone, or the water will definitely go down because you have the water can escape the glass. If you have a lid on it, it would not change its volume. Just to point out here that these interactions are intermolecular forces, and that different intermolecular forces we find in solutions will dictate how easy it is for this process to occur, for this being able to leave the liquid phase, which means you basically have to say goodbye to all your liquid friends, let go of all their hand holding, all those interactions to be able to go to the gas phase. So we're going to have some observations and explain them in different ways. And so the first observation that we have is actually the longest explanation, but probably includes my favorite graph of all time, which is a pretty big statement. So this observation is that vapor pressure increases with an increase in temperature. Okay. And so to understand what's going on here, we have to know the relationship of temperature and kinetic energy. And so kinetic molecular theory is explains this. Gases are a really nice system because they are very simple. There's very little intermolecular forces, or we assume there to be none. And kinetic molecular theory states that the average kinetic energy, or KE, is what we'll say. Average kinetic energy of gas particles is proportional to the temperature of the gas sample. Okay, so so the average kinetic energy. So that brings up a really good point, which is that if we have a particular gas sample, we don't have a homogeneous distribution, or we have a distribution of speed, which means you don't have just all gas molecules moving at the same speed. And so we can talk about this a lot of different ways, and kinetic molecular theory goes into more. So we know that, for example, the kinetic energy is equal to 1/2 mv squared. Now, velocity has a directionality component to it. So in general, for this chapter, we use speed instead of velocity, which is u squared, and this is the generally the root mean squared. I'm just saying this because your book might mention it or Alex might mention it. URMS is the root mean squared speed. Okay, and that is basically taking the average speed of of the particles. So anyway, it's we can do this in a graph, and this graph I think is super helpful to understanding a lot of things. So I really like this graph. So on the y-axis is number of particles, and on the x-axis it's the kinetic energy that a particle has. And so we said that there is a distribution of speeds that particles can have at given temperatures. So for, like, let's say temperature 1, we see this. So this is temperature 1, T1. We see that there's a distribution of speed. We see that down here, we have gas particles that have a very low kinetic energy, and that could be gas molecules that have a collision, and where they transfer most of their energy to another particle, and that particle then might be over here where it has doubled its kinetic energy, and it's on the high end, and then it collides again, and so there's some average for a given temperature. This spot right here is your maximum. This is your most probable speed, or kinetic energy. They are related, but they're different. And what we see is that as we increase the temperature, so let's say we have T2, and T2, temperature 2, is greater than temperature 1. What that means is that now we're going to shift this whole curve. We're going to flatten it, and we're going to shift it. So we're going to flatten it, and shift it down this way. Now the area underneath the curves, if I drew it correctly, should be the same because the number of particles is not changed. But now we are saying we still have particles that have zero kinetic energy, because that's always the case when you have collisions. But now we've changed this distribution of, now here, this was the highest kinetic energy you can go. Well, we've shifted this over when we've increased the temperature. Okay, now that's the first part. So understanding that two different temperatures, we have different distributions. We have broadened the curve, so it's like we have held this part, and it's like a string, and then we pulled the end, so it's flattened the curve. Okay, and so that's the first component. The second component, and this is really what makes this graph very useful, is that the intermolecular forces act as an energy barrier that the particles in the liquid have to overcome. So I'm going to draw that here. So remember that this is energy, kinetic energy. So this barrier right here is the energy. So in this case, kinetic energy needed to escape the liquid surface, and that is proportional. So that is to say, I'll write that right here. So more or stronger IMFs require more kinetic energy, which is this energy term. Okay, so for example, if we look here and we say, okay, how much energy? So if we look, if this blue line is the barrier, then I'm just going to shade in what proportion of molecules at T1 has the required energy. So this is number of molecules with enough energy to escape liquid. Now, if we remember right, so okay, so first you see this is like maybe 10% or something less than that. It's very small. Let's say 10%. If we go back to our picture here, so in order to evaporate, one, you have to be on the surface. So you have to be on the surface of the liquid. And two, once you're at the surface, you need to be able to have enough energy. So what this is saying is that if you look at all the molecules on the surface, on average, only about 10% are going to have the required energy. So it's just a numbers game. So if a small proportion of molecules has that required energy, then the vapor pressure is going to be very low at low temperatures. And if we look at the high temperature, to compare that and contrast that, so let's go shade in the number or percent of molecules that have required energy at T2. And now you can see maybe it's 40%. So now we can say that if we go back here and say, okay, well, how many molecules on the surface have the required energy? Well, 40%. So 40% have the ability to go into the gas phase. That should dramatically increase the number of molecules in the gas phase. Just statistically, it's more likely for them to do so if they're at the surface, and that would increase the vapor pressure, which is simply a measure of the amount of particles in the solution. So let me just write that down. So vapor pressure, I forgot to do that, is proportional to the number of particles in the gas phase above a liquid. And so that would increase, okay? And so this graph directly shows how, for a given intermolecular forces, which is the position of the blue line, we would have different percents of molecules that could have enough energy. Okay, so at lower temperatures, you just don't have enough energy. And now, if I want to do one other thing, is okay. So let's say the blue line's for water. Okay, and you can see it's pretty far over. It's a high energy barrier, and this is why water takes so much energy to boil. It's because it has to break all those intermolecular forces, all those hydrogen bonds, those hydrogen bonding networks have to be broken. But let's say we have a liquid like methanol, which still has hydrogen bonding, or even something that is like an ether or something like that. Maybe our what are we doing here? Let's go back here. Not sure what happened. Did something. Let's go back. Can we do that? No. Okay. All right.